Hello, everyone, and welcome to this talk on quantum machine learning on the Boolean cube for QKC Open House, October 19th, October 20th, 2022. First, I'd like to start by saying that this is joint work with my collaborators, Rudy Raymond, Muyuan Lee, and Antonio Mezzacapo at IBM Quantum, Tokyo and New York, respectively, as well as with Dylan Herman and Marco Pistoia from JP Morgan Chase, Future Lab for Applied Research and Engineering. The archive preprint is 2204.05286, and you can find version 1 of this preprint in there, and in a very short amount of time, we'll upload version 2 as well. So I'd like to start by discussing the motivation of what it means to study categorical data. So categorical data, as we all know from either classical or quantum machine learning, plays a very important role in a variety of algorithms and applications. And what it means to be categorical, it means to take discrete values. So for example, if you have a feature such as colors, color can be red, green, yellow, whatever, or it can be buckets of groups of ages, age group 1 to 10, 11 to 20, 21 to 30, and so on. So you are either in one bucket or another, and that is the discretization and hence the category. As far as finance is concerned, there are very many applications in things like fraud detection. Is a certain transaction on a credit card fraud, yes or no? Is a certain financial transaction money laundering or no money laundering, and so on and so forth. It also has a huge impact on credit worthiness and credit scoring. So credit score is also a bucketing game in which debtors are categorized in different categories of credit worthiness, say AAAs, AAs, and BBBs, and so on and so forth. So also very important applications over there. So we are going to consider supervised learning versions of these problems. So this means that we can either do like a classification. Is it going to be on this side, or is it going to be on that other side? Or, which is not the topic at all for today, a regression. That would be very fitting for continuous data, which is not at all the data that we'll be playing with today. We can map a single categorical variable to multiple binary variables by doing a binary expansion. So for example, 0 will get mapped to 0, 0, 0, 1 will get mapped to 0, 0, 1, and so on, for instance, if you do it up to 7. So that means that as long as you can expand a digit from base 10 to base 2, you'll always be able to find that map that takes you from categorical data to binary data. Moreover, supervised learning problems with the categorical variables do map to learning a function on the Boolean variables, or, which is the same thing, the Boolean cube. I'm going to tell you more about it in a second. What is this Boolean cube? So suppose you have only 2 binary variables, 0 and 1, which I'm going to denote by B1. B1 can take value 0 or 1. So you will be on a straight line. It's either 0 or 1. That's fine. What happens if you tensor this with itself, and you can actually now, instead of having 1, you have 2 variables, right? B1 and B2. In that case, you are spanning a bigger space, a space which is made of 4 vertices, 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so that is the Boolean rectangle, if you will, or Boolean square, rather. And you can still embed another categorical variable in there and call it B3. And in that case, you can still represent it geometrically with a nice picture. It will be this Boolean cube, and you have all permutations of zeros and ones, all the way from 0, 0, 0 to 1, 1, 1, 1. You can play this game a little longer up until probably B4 is the limit. B4 would be a 4-dimensional cube, which is called a tesseract, and that cannot be visualized in a 2-dimensional setting. So what you do is you project with a shadow. And just because you cannot visualize it, that does not mean that you cannot do quantum machine learning, or classical machine learning for that matter, or any kind of mathematics on that. So B4 would again have in a complicated geometric object all of the vertices of the data going from 0, 0, 0 to 1, 1, 1, 1. Okay, and you can map from a Boolean structure to the reals. And you can call this map F, let's say, and F will take a value on this categorical, on these Boolean values and map to a real, like let's say 0.1, minus a half, pi, square root of pi, anything that you want. So this is one of the functions that we'll be studying today. Machine learning problems involve categorical data are really prevalent across many domains. They almost don't need too much of a motivation, but let's discuss it anyway. The range of a categorical variable lies in a finite set, and thus each element can be mapped to multiple binary variables for each member of the set. Now, our goal is to perform supervised learning, and this amounts to converting or mapping the problem into learning the function, a function on the n-dimensional Boolean cube, as we were saying. And we're going to use this variational quantum machine learning. We're going to use two different techniques from VQLM to fit the function f so that it maps accurately from B4 to R. We show, these are the main results of the paper, we show that for any function on the Boolean cube, there will be, so it's an existence theorem if you want, there will be a variational quantum model with n qubits, which is based on a technique called phase embedding, such that the output of this model agrees with the target function for all of its inputs. So that is kind of very nice because it wouldn't be helpful if it doesn't agree with all the inputs, but it has to do this task in a certain sense, in a certain quantifiable sense, better than the classical algorithm. And this is something that we are going to get into very soon. Then we'll switch gears and take a different technique, which is called quantum random access codes, QRACs for short. And we will also demonstrate that for any function of degree d, if this degree d, if you take the number of, if you take n and you divide it by 3 and you take the floor of this, in case n is not divisible by 3 on the Boolean cube, then there will also exist an ensemble on the variational linear quantum models with n divided by 3 qubits based on this QRAC. And the result is such that the output of the ensemble agrees again with the output of the target function for all of its inputs. So looking at this, you might want to say, oh, I want the QRAC immediately because I'll have to use fewer qubits. Okay, there's some caveats to that. And we're going to test these two results for low degree functions. I think it was degree 4, 5, or 6. I will see it very soon on the Boolean cube with IBM superconducting processors, quantum processors. So now that we've motivated these, I think we can advance to the mathematics. And we can say that the set of all functions on the Boolean cube forms a vector space of dimension 2 to the power of n. And in this, it's not any ordinary vector space. It's one embedded with an inner product, so Hilbert. And it's what you would think. You take a function f, embedded in a bra, take a function g, embedded in a ket, you close the bracket, and it's going to be the sum over f times g, and f applied on all the whole bit string, and g applied on the same bit string, and then you average by 2 to the power of n. Another concept that we're going to be needing very frequently is that of the Fourier transform of a Boolean function. So that will always be denoted with a hat. And in order to define it, I first need to introduce the character or Dirichlet character chi s of b. So it's defined as the product of -1 to the power of bi, where bi is in the string in the vector b, but the i's are chosen such that si is always equal to 1. So that will put a restriction on how many of these will be 1s and 0s and so on. So the Fourier transform is, as you can see, it's an inner product of f and chi. So f acting on b, applied on b, and chi of s also applied on b. Now, a K-junta has a really interesting wording. It's a military term. Is a function on this Boolean cube whose output only depends on k of the input variables. So that means that the other n minus k variables will not have a say. So it's completely dominated or dictated by these k input variables. Okay, so now suppose that n in brackets, such as I'm writing in here, is the set of 1, 2, all the way up to n. And suppose that this set, J is a subset of this, and it contains k indices corresponding to the input variables that the junta depends on. The Fourier transform of a k junta can only be non-zero on the elements from this set over here that I'm describing. So it's the set of all s's belonging in the Boolean cube, okay, such that for all I in this set n, that goes from 1 to all the way up to n, Si equals 1 implies that I belongs in the set J. So that means that you can do better than get an upper bound. We'd actually get an exact result. So the cardinality of J will be the number of terms in the junta. So juntas are useful in learning theory for modeling learning tasks where the data can be explained only by a subset of the available features. So you can get rid of a lot of features that are not necessarily, or that are in fact not needed. So it helps a lot with data cleaning, data engineering, and so on and so forth. So scenarios typically occur when applying supervised learning to real-world data sets very frequently. Now, the Hamming weight is your distance from 0 to your letter in the alphabet, okay, like a typical, absolutely standard Hamming weight. And the degree of f is then defined as you make up a set, W of s, where W is the Hamming of s, such that for all s in the Boolean cube, the Fourier transform is not 0. Okay, so you make up that set and you take the maximum of that set, and that will be your degree. Okay, so now variational quantum machine learning, as the name implies, will have continue. Excuse me. Will also have a parameters that make up the gates in the circuit. Okay, so what this means is that you will have a state preparation first. Okay, X will be mapped to the amplitudes of your register, and it will undergo a unitary transformation that depends on gates. And these gates will be rotations typically, or controlled rotations, 1 or 2 qubit rotations. And what makes it parameterized is those angles. So perhaps maybe theta would make more sense to be written with an arrow on top to indicate that it's a set of angles. And then you make measurements, like some sort of tomography or some sort of selective measurement, and you're going to get your you're going to go back to classical, because this part here is quantum. The blue part will be classical readout. Okay, so you're going to have an output of a cost function f, and excuse me, the output of your function f, and you're going to compute its cost. Okay, so that will be the expectation of y minus the minus your function, and maybe it might be a moment. It might be the first moment, the second moment, so it might be a mean or a standard deviation or whatever, what have you. Okay, and you're going to make a choice. Are you happy with this or are you not? And if you are, then that's it, you're done. Otherwise, you're going to update these angles again, and you're going to go back to preparing the state, and you're going to run the whole variational quantum circuit again with the updated angles. And the process keeps repeating itself until you are satisfied with your cost function. Okay. Next, when applied to supervised learning, VQML consists of using these PQCs. You have as building blocks the embedding blocks and the trainable blocks, okay, which is where your angles are going to be. And your input data will be a set potentially from Rn, and it'll be stored on classical memory and can be embedded in a quantum state by utilizing a quantum embedding technique, such as the ones that you see state preparation or amplitude preparation, and so on and so forth. The variational linear model is this function f. So depends on your angles, depends on x, and is defined as the trace of this operator h, which is an operator that belongs in the span of. So it's made of poly gates, right? Identity and poly gates. And what you do is you take these poly gates and you tensor them many times, m times. And the span of that is where your H operator will reside. Okay, and there's another W, which is the UPQC, and another rho, which is defined as U acting on your zero registry, and then as a get, and then U dagger, so the Hermitian conjugate acting on your zero registry, but as a bra. Okay, so you can make out these quantities, and you keep them in mind for the calculations that will follow shortly. Now, phase embedding that we are going to investigate was actually, we're not the first by any means. It was already considered by Maria Schultz for continuous valued inputs. So you might ask, you would think, well, if she's already done it for continuous, what is the point of doing it again for discrete values? Well, the thing is that they showed that if the phase embedding is repeated r times, sequentially or in parallel, then the output of the variational model is expressible as the rth, should not be a cubic here, the rth partial sum of a Fourier series, such as this one right here. And X is your n-dimensional input. So the trainable blocks and observable controls are these Fourier coefficients over here, the C omegas. If we assume the freedom to choose arbitrarily deep trainable blocks, which is, you know, quite an assumption, and an arbitrary observable, then a model using this embedding can approximate any function on the circle, 0 to 2 pi with L2 norm, to arbitrary small error using sufficiently many repetitions R. Instead, what we do in this paper is we show that a variational linear quantum model using the phase embedding, which implies that R is equal 1, can express any function on the Boolean cube if an arbitrary observable can be used. So I don't have to repeat it that many times. It's okay to just do R equals 1 for us. So less expressive data, or data that has more restrictions, but fewer repetitions. And for her, perhaps better data, but more repetitions. Okay, so moving on, the linear quantum models. For the variational linear model, we already discussed, you have your trainable, you have your zero registers, and then trainable, and then W. And for the quantum kernel methods, what you're going to do is you're going to have a unitary transformation, and then it's Hermitian conjugate unitary transformation. First, you're going to output the expected value, and you're going to compute the loss and update the parameters, just as we discussed. But with the quantum kernels, what you're going to do is output a probability distribution of observing all zeros. And the kernel method could be, for instance, a support vector machine, or a classification and regression, or something like that. The Boolean phase embedding is a variational linear quantum model. Okay, so what we're going to do is going to use 6, and we want to have a number that is divisible by 3, so that we can compare it later to QRAC. So what will be 6 qubits starting in the 0 position, then applying these X gates on them, and then a Hadamard. So that's my UB component. And this ansatz over here is, I believe it's called the universal ansatz without cyclicity. So producing a layer of rotations in Y, a layer of rotations in Z, and entangling qubits 2 at a time. But qubit, so by that I mean that qubit 1 gets entangled to 2, 2 to 3, 3 to 4, and so on and so forth. But when we get to 6, it does not recycle itself back to 1. Okay, that's kind of an important feature. And you can repeat this as many times as you want. Here we're going to do it 1, 2, 3, 4 times. Well, 3 times, 3.5 times if you want, and then measure. For every function on the Boolean cube, there exists a variational linear quantum model with a phase embedding that can learn it. That was the result. Okay, the QRAC is less expensive in terms of quantum resources. And as we said, if you take 6 and you divide it by 3, which is the feature of the paper, then that will make 2. Okay, so we don't need that very many qubits. Instead of 6, we're going to use 2. The UB portion is similar, because it'll be made of RY and RZ rotations, but there will be a much more complicated angle going in them. And this angle, of course, will depend on the binary strings. The W component will also be much shorter, made of RYs and RZs, and with embedding, with entanglements in between them. Okay, the ensemble of the models will be such that you have this data, labeled or unlabeled, and it'll go into different models, and then you make a prediction. Okay, so any function on n dimensional cube with degree less than or equal to n divided by 3 ceiling of that can be learned by an ensemble of QRAC embedding based variational linear quantum models on n divided by 3 qubits. For simplicity, let's assume that n is divisible by 3. And a k junta with k less than or equal to n divided by 3 certainly satisfies this condition. So the experiments on quantum hardware, sorry that this did not come out very clear. I think the degree here is going to be, so G3, A1, its coefficient, minus 1 to the power of B1, A2, and A3 also as coefficients of the minus 1s. When doing this with phase embedding on the Guadalupe machine, we were able, and on a simulator as well, we were able to get fantastic predictions. Okay, the targets match exactly what the simulation predicted and what the hardware predicted as well, or nearly, in order to account for noise. The QRAC embedding was surprisingly similar as well. Perhaps a little bit more precise even on certain Fourier coefficients, although this one was kind of, it was missed by both phase embedding and QRAC. Okay, the coefficients of A1 were 1/2, A2 was minus 1/10, and A3 was 1/4. You can change them and you'll get slightly different results. And we picked fractions that helped a little bit with the noise, I have to admit. Now, with a much more complicated 6-bit experiment, we're taking more complicated, more complex truth functions here, minus 1 to the power of B1 plus B4, B1 plus B5, B2 plus B4, and B2 plus B5. And for the most part, the results were very satisfactory. For the phase embedding, there was just a little bit too much noise, so therefore we decided to go for simulator, and the simulator did agree very much with the targets, and the Fourier spectrum was also very satisfactory. The QRAC, because it uses fewer qubits and it's not as deep and so on and so forth, it lends itself very well for the hardware, and most of the results were surprisingly good, except perhaps for this outlier over here. Okay, so future directions for study are, study the ability of such models and generalize to unseen data. One thing that we didn't touch upon was the quantification of the required number of training samples needed to learn these functions. So something could be said about that. And benchmarking these models that use QRAC embedding. Identify cases where we can exploit the structure of the problem to design efficient algorithms. And the size of the circuits, just how shallow can they be, or how much do we have to go in terms of depth. Thank you so very much for your time. It's always a pleasure to present this work and future work at KQC. Please don't hesitate to contact me if you need to. You can reach out to me at nicolasrobles@ibm.com, and you can find out more about IBM Quantum at ibm.com/quantum. Thank you so much for your time.